Okay. All right. Distribution of molecular speeds. Let's take an equation from the literature and then analyze it. We will not be deriving this Barracuda equation. It's huge. It's very intricate, and we can derive it from first principles in a very clear way. But this is what you get. So if you look at this equation on the left-hand side term, dnc by n times 1 over dc. So dnc by n is our probability, and now 1 over dc means it's dividing with the interval width. Therefore, you get the probability per unit width. So that's it. Okay? The probability of a molecule having certain velocity per unit width. That's on the left side, unit width. So 4 pi is of course constant, m, the mass of the gas particles, divided by 2 pi, k, this is the Boltzmann constant introduced for the first time, okay, T, the absolute temperature scale. This whole fraction is raised to the power 3/2. At constant temperature, remember, this part is going to be constant mass, molecular mass, and constant temperature. This can be written as a constant. Multiplied by c squared, square of the speed. Okay, here this probability is going to increase as square of the velocity c, e to the power, parenthesis in the exponent, minus mc squared over 2 kt. Minus mc squared by 2 kt. So now m snuck into this again. It's the molecular mass. C is the velocity, and k is the Boltzmann constant, T is the temperature. So this is a complex equation, and this is a distribution function. How do we know that? Now, if you now plot this, the left-hand side value is function of right-hand side values as a function of velocity c, then you will see a distribution curve like this. So probability p as a function of c. On the top, I have simplified the expression on the left side. So probability p, now we represent by capital P. Lower p is the pressure. The capital P is constant A, c squared. So that's the quadratic term that I just showed to you. So initially, it's going to increase quadratically. And e to the power minus mc squared by 2 kt. That's exponentially decaying. So you have a product of two functions. The first function in this equation is c squared, quadratically increasing with c. The second function is exponential, e to the power minus mc squared over 2 kt. The function is decaying exponentially. We are multiplying the two to get the net expression. So what does this mean to us? Let's analyze it a little bit more. So let's say the value of c gets close to 0. Okay. So what's going to happen? As the value of c gets close to 0, so dnc by n 1 over c, 1 over dc equals to 4 pi m over 2 pi kt 3/2 c squared. So as c approaches 0, the exponent becomes nothing. It becomes e to the power 0, right? E to the power 0 is 1. So we can approximate that the left-hand side in the top equation will be essentially a quadratic equation in C. E to the power minus mc squared by 2 kt. When c goes to 0 almost, then e to the power 0. Particularly k and t are dividing, so it becomes even smaller. M is very small as well. Therefore, e to the power minus mc squared over 2 kt approaches 0 much faster than c itself. So as c is approaching 0, e to the power minus mc squared by 2 kt approaches even much faster. So e to the power 0 is 1. So at low values of c, we should see a quadratic function only. Okay, that is like this. Distribution per unit width will rise quadratically. So if I were to plot probability on the y-axis, the molecular speed c on the x-axis, at low c values, That's what you see, a quadratic expression, approximately quadratic, green curve. Okay. Now, if the C goes to very high values, right, very, very high values, then the exponent takes precedence. And so P is A star, so that's your thing, e to the power minus mc squared by 2 kt. And this whole function goes to 0. Whole function goes to 0. Even though you have c squared, because you're multiplying with this exponent, which is close to 0. Okay. So in the first case, the exponential function is reduced to 1. In the second case, the exponential function is going to 0. So the probability goes to 0 at infinite value of c. So at high c, you have the blue curve, and so the function decays. So in other words, in between values, there is a balance. So one extreme, right? And c approaches 0, you have c squared is going to be a very small value. So it also, of course, goes to 0 on this side, but increases initially as a quadratic. When the c squared becomes substantial, then the exponent starts to kick in, and the exponent makes it decrease. So c squared is increasing, exponent is decreasing. So you have two functions multiplying each other. That's the net result. All right, so let's look at this and try to figure out what's the effect of mass and what's the effect of temperature on this distribution function. So dnc is equal to, I've rearranged it, 4 pi n. N is on the left hand side. This fraction raised to the power 3/2 c squared we have discussed, e to the power minus mc squared by 2 kt we already discussed, multiplied by dc. The dc was on the left side in the previous slide, so now we'll move to the right side, so that now I can integrate on both sides. Why? Because on the left side I have dnc, so I can integrate that. On the right hand side I have terms of c and dc, and all the others are constants. Then I can integrate that pretty easily. So, but you just look at this and what do we get out of it? It's just examining this, the probability on the y-axis, velocity on this z-axis, and now if we have very heavy mass versus very light mass, how does the distribution function change? If you have very heavy mass, then we know on the right hand side m is in volts, and so the function rises quickly and also decays quickly, because you have m before c squared, and we also have m in the exponent of the exponential decay function as well. So both it will rise fast and the decay fast as well. If you have a value for m that is very small, and light particles, then it's going to rise slow and it's going to decay slow. So the yellow curve represents for gases that have lower mass, and the green curve represents the distribution function for gases that are heavy. Okay, so it's very simple to look at the expression above and then write that in the bottom. What happens to the velocities distribution when we change the temperature? So you have, say, a blue curve, that's room temperature. This is what we're seeing. And now you can recognize that the T is in the minus e to the power mc squared by 2 kt term, that is in the negative exponent of the exponential. So the exponential is raised, so as you raise the temperature, the value of the exponent is going to become small. That is, mc squared by 2 kt becomes smaller and smaller as you raise the temperature to higher and higher values, because t is in the denominator of the exponent. So as this exponent becomes smaller and smaller, the exponential function is dying slower and slower. So it will be rise, and then the decay will be slower. Okay, so the rise will be slow and the decay also will be slow. That's the key thing to think about. Okay, because the temperature is in the denominator. So this is an important part in looking at this stuff. All right, so the velocity distribution depends mass, also on the temperature, of the gas in these particular ways. Now let's look at the distribution of velocities versus average velocity of the gas particles. Previously, we calculated root mean square velocity of the gas particles. So now, one of the very useful consequences of distribution functions is that you can calculate the average, you can calculate the width of the distribution, and you can calculate the probability at any given point, and so on and so forth. So this is the same expression we talked about in the previous slide. dnc equals to a function, a constant raised to power 3/2 at constant temperature, c squared, the quadratic term, e to the power minus m c squared by 2 kt, the exponentially decaying term, multiplied by dc. So now, as we discussed, we can integrate on both sides if you wish, right? So if you were to then integrate, you can get the average. You can get the average number of particles having certain velocity c, that is shown in the left hand side, and then that is, remember, if I were to take dnc and divide by n, then I get the probability. So dnc is given, and then I'm going to divide with n. So integral 4 pi n m over 2 pi kt raised to power 3/2. The rest is the same. Okay, simply divide with 1 on both sides, right and left side. So n and n will cancel away, and you can integrate this quite readily, and you can look it up in the book, you can look it up in the calculus tables, and then put the integrals on, integrated expressions on. So that turns out to be square root 8 kt over pi m. So this is a deduced result. You don't have to work this out, but it'll be useful if you worked it out. So square root 8 kt over pi m is the average velocity. Now remember, this is not root mean square velocity, it's the average velocity. I can manipulate this a little bit more and get RT instead of KT. We simply Boltzmann constant K, when you multiply with Avogadro's number, you get R. So this is something we're going to do some other time, not at this point. So 8 RT over pi m. Capital M in the bottom because Avogadro number multiplied by mass of a gas particle gives you the molar mass. Okay, and same with Boltzmann constant multiplied by Avogadro's number gives me gas constant R. So this is not the root mean square speed, but this is the average speed. Also the most probable speed, as well as RMS speed, and they all can be estimated from Maxwell distribution. So this is one of the useful properties of distribution functions in physical chemistry. So if we know the molecular speed distributions, then we can also compute kinetic energy distributions. Now this is an important deduction because kinetic energy is a manifestation of the motion of molecules, and we know the kinetic energy is given as half mv squared, right, from Newtonian mechanics. So if I know how the speed is distributed, then I know how the energy is distributed. Right? So why is this important? Remember, in the beginning we said the energy of the gas sample is critical to determine if we're going to expect a chemical reaction to take place or not. Because does the gas molecule have enough energy to go over the barrier to give rise to the product? And these sort of questions we're going to raise later on. So I would like you to read about equipartition of energy, degrees of freedom, Maxwell-Boltzmann distribution. So these are important topics. I'll not be covering in the slides here, but like you to read. And as I said before, we want to enhance your independent reading skills and learning skills. So this is our simple assignments to think about these and read about, and then we can discuss some of these issues not clear to you. So then we also will say I'll work out two examples from the book which use any of the above equations. And so just two examples, and you can send your responses to me by PDF as a PDF file.